Hi everyone. So in this video, basically I thought I will go through some of the concepts we discussed in lecture one, but I'll go through them a little bit more slowly. I will also give you some examples to hopefully clarify some of the things we discussed in lecture one. So the main topic we discussed in lecture one was that there are different kinds of fluxes that we can describe for each species. So we described that mass flux, small ni, has two components. One is the convective flux and the other is the diffusive flux. So recall that this is the convective flux and this is the diffusive flux. And this is again for a species I, right? At the same time, we also describe this velocity vector V. So velocity vector V is mass averaged velocity. Okay, so this is the mass averaged velocity. The units of Ni are kg per meter square second. Okay, the units of rho I are kg per meter cube. Units of V are meter per second, and the units of Ji are kg per meter square second. Okay, and then in the class, we also discussed that you can describe J by small j by Fickian diffusion law. So I will not discuss that in this video. The main goal is we know that this is an equation where we have described Ni, which is the mass flux in terms of a convective part and a diffusive part. Now, we also said that this is V is mass average velocity, which means that V is defined as sum of Ni by sum of rho I. Okay, and this is the definition of V because we are basically finding an average velocity as by weighted by mass. So the density is describing the mass of mass averaging. So you can also write this as Ni by rho, where rho is the total density, where you can sum all rho. Okay, so this is the description that we have. So one thing we can do here, and this is something we did not do in the class, is that we can simply say, let's say I is simply A and B. Okay, I is simply A and B. There are only two species, and let's try to apply this result, which will hopefully clarify some of the elements of this description. So what this means is that Na is rho A times V plus small ja, right? And similarly, Nb is rho B times V plus Jb. Okay, so we know this that we are basically substituting I as A or B, and we have described this result. Now, if we sum these equations, you will get that Na plus Nb is rho A plus rho B times V plus Ja plus Jb, right? So now we get, basically we have just added the two terms. Now you can also see that I can call this term as rho V because rho A now is rho A plus rho B. You can see it from here, right? So now if I can just substitute as this as rho V plus Ja plus Jb, and this I can substitute as sum of Ni, right? This is sum of Ni essentially. So this is sum of Ni, right? So now we know that sum of Ni is actually equal to rho B, which means that these two terms get cancelled, or the final result we get is Ja plus Jb is equal to 0. Okay, and this is important that basically what we have done is that we have derived this result, which I basically gave in class as something that you should know, but you can actually derive it by simply seeing that the definition of mass average velocity ensures that the sum of the diffusive flux of the species per weighted by mass, basically this is in mass units, is equal to 0. Okay, so this is the first thing that we have learned by doing a simple exercise. The second exercise I want to do is I want to divide this by MA, which is the molecular mass of A. And I want to divide this equation by MB, which is the molecular mass of B. Okay, so we can do that. And what we will get is Na by Ma is rho A by Ma V plus Ja by Ma. Okay, so I've done this, and basically this is what we call as capital Na. This is the same thing, just that we have now changed from kg per meter square second to mole per meter square second, because the units of Ma are kg per mole. So the units of Na are mole per meter square second. That's all we are doing here. Similarly, we've changed from density to concentration. So this was kg per meter cube, and this is mole per meter cube. And finally, we have again also gone to molar units. So the capital description of the vectors is the molar units. Similarly, we can also write NV is CBV plus JB. So now that we have described NA and NB, now let's try to sum these terms, right? So if we sum these two terms now let's try to sum these equations. Right? Now, if you do that, you will get NA plus NB is equal to CA plus CB times V plus JA plus JB. Okay, so if you basically what I have done is just converted from kg per meter square units to mole per meter square second unit, and then I'm just again using this result here, right? Now you can imagine that you can again substitute back the value of V. This is essentially nothing but CA plus CB. And do not forget this velocity is mass average velocity. So this, as we had described, is NA by NB by rho A by rho B, right? So again, I'm going back here. So the velocity, I'm just simply describing summation of N by summation of rho. So there are two components. So it's NA and NB and rho A and rho B. So that's what I'll have written. Sorry, there is no bar here. This is just a scalar. Rho A plus rho B, right? Plus JA plus JB, right? And why am I doing this? The reason I'm doing this is now I can write this finally as NA by NB is equal to CA plus CB times NA MA plus NB MB by CA MA plus CB MB, okay, plus JA plus JB. And what you can do yourself is you can now subtract. So now everything is in terms of C and N and M. You can convince yourself that JA plus JB is not equal to B, is going to be 0 unless there are some special conditions apply. So this is not equal to 0, This is not always true, but most likely this will be the case. Unless there is some special conditions, it is possible that this is true, but this is not a rule. Like this was a rule that J plus JB is 0. Similarly, the molar flux, the summation of molar flux is not going to be equal to 0, okay, based on the mass average velocity. Okay, so I hope this sort of gives some more clarity that all we have done is we broke down the flux small ni into two parts, convective and diffusive, where we have described velocity as the sum of flux, the sum of density. And if we simply add the terms, we can derive the fact that Ja plus Jb is equal to 0. And if we change the units from mass to moles just by dividing by molecular weight, we can also convince ourselves that the molar flux based on mass average velocity is not equal to 0. Okay, so you can try to simplify this, but you will see that this does not really come out to be 0. Okay, so now let me try to go further, and now let's go back again and see that we have described Na till now. We have described Na as CaV bar plus Ja, right? But in class, we have also described that it is possible to say that Na is actually CaV molar plus Ja. So again, I'm assuming that I is equal to still A comma B, still a binary system. Similarly, NB will be here. This is also Ja molar. So the left-hand side, which is this term here, stays the same, but the way you break it down into two parts are different. So this is also convection and this is diffusion, but the convection part is now not based on mass average velocity, it is based on molar average velocity. So what do we mean by that? Let's take a look. So this is the how we can write it into molar fluxes. Okay, and now if you go here, the way we described V molar would be similarly, we'll say sum of Ni, or here in this case Na plus Nb, Na plus Nb, right? And we'll divide this by Ca plus Cb. This is the definition of molar velocity, because basically we are saying we'll take the molar sum and divide by the concentration. Please contrast this with the other description where we have taken the sum by mass and divide by density. So that's the difference, right? And we have done this. So basically we can write this as summation of Ni by summation of Ci, or sometimes you can call this summation of Ni by C, where C is basically nothing but summation of Ci. Okay, so okay, we have described this molar velocity. Now what we can do is, again, we can add these terms, and we can see that Na plus Nb is equal to Ca plus Cb times V molar plus Ja molar plus Jb molar, right? This implies that, and we know that the Vm is nothing but Na plus Nb by Ca plus Cb. So I'm just taking it from here and substituting it here, right? Plus JAM plus JBM. Okay, that's all I'm saying. And you can cancel this out. This can cancel this out, or JA molar plus JB molar is equal to 0. So the diffusive flux on the basis of molar units is 0 if we use the velocity based on molar values, or if we basically average based on concentration. This is a less common phenomena. There are some cases which you will see in the later lectures where you actually use this averaging. More commonly, you use this case where the molar flux is based on mass average velocity is actually not equal to 0. Okay, so I hope this gave you some clarity of how we basically break down the flux into two parts, convective and diffusive. Typical idea is to use the mass average velocity, where we can say that the small j, summation of small j is zero. And if we basically we divide everything by molar mass, we get into capital J, still based on mass average velocity. The summation is not equal to zero. The second definition is where basically we just directly define based velocity based on molar average, which does give us that the sum of the diffusive flux is zero. So this was what we discussed in class in a bit of a rush. So I hope this video helps. I'll also create another video in which basically I'll give some quantitative numbers to these different symbols going around. And I think that will bring further clarity into how the sum will look like, how these different terms relate to each other. Okay, so watch out for that video, and I hope this video helps. And I look forward to seeing you in the next video.